Welcome back, students. So in this video we will discuss about energy. So we know the meaning of energy. It's a commonly used word, work, energy, but in physics it's having different meaning. But in the meaning of energy and work in physics is different. So we may say like this, that person is full of energy. That person is full of energy. Or a patient is not feeling well or is feeling restless. That means the energy is not there. Okay, or he has no energy. So the meaning of energy in physics is different. So let us consider some examples. Before that, sun is the ultimate source of energy of our earth. The sun is the biggest natural source of energy to us. Most of our energy sources are derived from the sun. We get energy from the nuclei of an atom, from the interior of the earth, and also from the tides. We will get energy. Okay. Now let us consider some examples. Yeah. First one. When a cricket ball just touches the stationary stump, nothing happens, or the stump will not move, or the wicket will not move if it just touches the stump. But when the same cricket ball hits the same stump at a fast speed, then the stump are blown away. So we say that fast moving cricket ball has the capacity to blow the stump away. The fast moving cricket ball has the capacity to blow the stump away. The energy possessed by the fast moving cricket ball is measured in terms of its capacity of doing work. So when a cricket ball just touches the stump, the stationary stump, then nothing will happen. If a fast cricket ball touches the stationary stump, then the stump may blow away. The reason is that the fast moving cricket ball is having a capacity to do work, or is having a capacity to blow away the stump. Then next one example, if we touch the hammer with on a nail to drive into a piece of wood, whether it is possible, can we drive the nail into the wood by simply touching the hammer on the nail? No. So we need to raise the hammer and then we need to touch it. We need to raise the hammer vertically above the head of the nail, and then we need to strike the hammer on the head of the nail. Then that nail will drive into the wood. So if you raise the hammer, then you are doing some, or that raised hammer has the energy to drive that nail into the wood. So if you simply touch the hammer on a nail, the nail will not drive into the wood. If you raise the hammer above the in a vertical position above the head of the nail and then you strike it, then the nail will go into the, or the drive into the wood. So, this hammer is having a capacity to do the work, or it's having that energy to do that work. Here the work is to drive the nail into the wood. So, that raised hammer is having the energy to drive this nail into the wood. Next example, you can see a spring. Normally we use that spring in toy cars. So, that spring is this is the normal shape of the spring. If I draw the shape, this one is the normal shape of the spring in a toy car. If you wind the spring, then you can see this is the shape. If you wind the spring, then that is the shape of that spring. So, the spring is that spring is inside a toy car. By winding the key, we wind up the spring inside the toy car. On winding, the spring will get coiled. The spring will get coiled more tightly. That means there will be a change in the shape of the spring. There will be a change in the shape of the spring, means the shape of the spring decreases or it reduces the size. The work done in winding the spring gets stored on it in that tight form. Means when we wind the spring, the energy will be stored in that spring. When the wound up spring gets released to return to its original position, it turns the wheel of the toy car and makes it run. Thus we say that the wound up spring can do some work by virtue of change in its shape. So, normally this type of spring is there in toy car. When you wind the key of the toy car, the spring, the spring will wind up. Means there will be a change in the shape of the spring, or the coil will wind tightly. The coil will be wind tightly, or the coil will get more tightly, and some work is done. When the work done in winding the spring will be stored in it. When you wind it, that work done will be stored in it, and when you release it, and when you place that toy car on the floor, the toy car will move. So, by that time what will happen? The spring will go back to its original position or original shape. The spring will go back to its original shape. Okay. So, that change in shape has some capacity to do work, or it's having some energy. That energy can be utilized to do some work. Okay. So, in all these cases, that cricket ball, that hammer and that coil has a capacity to do work. Or some energy is there in that can be used to do some work. So, energy means it's a capacity to do work, or its ability to do work. That is known as energy. Its capacity to do work, or its ability to do work. The amount of energy possessed by an object is equal to the amount of work of it can do when the energy is released. Then one more example I will tell you, that is when a balloon is filled with air and when we press it, we notice a change in its shape. When a balloon is filled with air, and when you press it, you can see that there will be a change in the shape of that balloon. As long as we press it gently, it will come back to its original position if that force is removed. As long as if we press it gently, then if you remove that force, then that balloon will come back to its original position. Then, however, if we press the balloon hard, then it may even explode with a blasting sound. If you press it hard, then what will happen is that it will burst. It will explode by producing a bursting sound. Okay. So, in all these examples, an object having a capacity to do work is said to have energy, or energy means ability to do work. The object on which the object which does the work will lose the energy, and the object on which the work is done gains energy. The object which does the work will lose the energy, and the object on which the work is done will gain the energy. Just underline that in your textbook, page number 149. An object that possesses energy can exert a force on another object. That energy will be transferred from one object to another. An object that possesses energy can exert force on another object. That means the energy will be converted from one object to another object, or it will be transferred from one object to another. The second object may move as it receives energy and therefore to do some work. So, here this is the first object. And the nail is the second object. So, the hammer will transfer the energy to the nail, and the nail will move. The nail will drive into the wood. That means the second object may move as it receives the energy and do some work. So, first object is a hammer. The hammer is having the ability to do work. So, hammer, when we strike the nail with the help of a hammer, the hammer will give the energy, will transfer the energy to the nail, and the nail will drive into the wood. Thus, the first object has the capacity to do work. This implies that any object possesses energy can do work. Okay. Now, the SI unit of work is joule. So, the SI unit of energy is also joule. SI unit of energy is also joule. So, 1 joule of energy required to do 1 joule of work. 1 joule of energy is required to 1 joule of work. 1 joule is energy required to do 1 joule of work. Then higher units are there. Kilojoule is there. 1 kilojoule is equal to 1000 joule. 1 kilojoule is equal to 1000 joule. Different forms of energies are there. Means we can convert one form of energy to another form of energy. You know, work is a scalar quantity. Energy is also a scalar quantity. Energy is also a scalar quantity. SI unit is joule. 1 joule is the energy required to do 1 joule of work. Higher units are kilojoule. 1 kilojoule is equal to 1000 joule. Now, different forms of energy is there. Light energy, chemical energy, mechanical energy, then sound energy, light energy, electromagnetic energy. So, different types of energy or different forms of energy are there. So, we need to consider mechanical energy. That's mechanical energy is divided into two, kinetic energy and potential energy. Kinetic energy and potential energy. So, kinetic energy. Here we will discuss about kinetic energy. So, we know a moving object can do work. A moving object. Here the stem is stationary. The ball is moving. Here the nail is stationary. The hammer is moving. So, a moving object can do work. A moving object can do work. The object which is moving faster can do more work than an identical object which moves slowly. An object which moves faster can do more work than an identical object which moves slowly. So, when you hit the nail with a hammer slowly, when you just touched it, whether the nail will drive into the wood? No. If you move it, if you strike it, then the nail will drive into the wood. Okay. So, a moving bullet, a blowing wind, a moving car can do some work. Okay. A speeding stone can also do some work. So, a falling coconut, a moving car, a rolling stone, a flying aircraft, flowing water, blowing wind, a running athlete, etc. possess kinetic energy. Etc. possess kinetic energy. So, if movement is there, then that object possesses kinetic energy. So, kinetic energy means the energy possessed by an object due to its motion. The energy possessed by an object due to its motion, that is known as kinetic energy. A moving bullet, a moving aeroplane, means flying aeroplane, flowing water, all those things is having kinetic energy. Okay. So, in short, kinetic energy is energy possessed by an object due to its motion. Due to its motion. So, the kinetic energy increases with the increase in speed of the object. If the object is moving faster, it is having more kinetic energy. If the object is moving slower, it is having less kinetic energy. Okay. So, now we will derive the equation for this kinetic energy. Before that, I will read some more examples of kinetic energy. The running water possesses kinetic energy and can run a water mill. The running water is having kinetic energy, and that energy of water is used to generate electricity in hydroelectric power stations. Okay, water will be stored in a dam. Then from the dam, the water will flow through pipes known as penstocks and reaches the generating station. So, the flowing water. So, the energy possessed by the flowing water is used to rotate the turbine and electricity will be generated in hydroelectric power stations. Moving wind, moving air, that is known as wind. So, that wind is having kinetic energy, and that kinetic energy is used to generate electricity in windmills. Moving air, that is known as wind. So, that wind is having kinetic energy, and that kinetic energy is used to produce electricity in windmill. A bullet fired from a gun possesses kinetic energy and it can pierce into a target. Okay. So, now we will derive the equation for kinetic energy. We need to derive the equation for kinetic energy. Kinetic energy. So, here you need to consider an object of mass m. Initially the object is at 0, so its velocity will be 0. You are applying a force on this object. So, it will get displaced. This point is A. It gets displaced to a point B. So, this much is the displacement. So, its velocity is V. So, when it travels from A to B, its velocity is V. Okay. So, we need to derive the expression for kinetic energy. So, first you need to consider an object of mass m moving in a straight line with a constant velocity. For this, the kinetic energy of the object is equal to the work done in imparting it to a velocity v. So, the kinetic energy will be equal to the work done in imparting it to a velocity v. Suppose initially the object is at rest, so its velocity will be 0. Let a force be applied on it so that it will attain a velocity v starting from rest. It will attain a velocity v starting from rest. Let the acceleration produced in the object is a and the distance moved by the object as it attains this velocity v is s. So, you have to consider an object of mass m. Initially the object is at rest, so its velocity will be 0. You are applying a force on this object, so its velocity changes from u to v. So, it will cover a distance s in order to attain that velocity v. So, now we will derive the equation, that is from third equation of motion. From third equation of motion that we studied in first chapter. In the chapter motion, we studied v square minus u square equal to 2as. V square minus u square equal to 2as. That is the third equation of motion. Okay, that is the third equation of motion. Now, from this equation, we will write an equation for s. We will write the equation for s, that is s is equal to v square minus u square by 2a. V square minus u square by 2a. Okay, that is the first equation. S is equal to v square minus u square by 2a. Now, according to second law of motion, according to second law of motion, F equal to ma. According to second law of motion, F equal to ma. Name it as second equation. Now, we studied about work. Work is equal to force into displacement. So, we will write that equation. Work is equal to force into displacement. Now we will substitute for F, W equal to F into S. Now we will substitute for F and S. F equal to MA into S, V square minus U square by 2A. So force is MA into S, that is V square minus U square by 2A. So A is there, A will get cancelled. So we will get it like this, M into V square minus U square by 2. V square minus U square by 2. This one I will split it like this. It's equal to half into M into V square minus half into M into U square. Half into M into V square minus half into M into U square. Okay, half into M into V square minus half into M into U square. Now, here initial velocity, M is the mass, V is the final velocity and U is the initial velocity. So, initial velocity is 0 because the object is at rest. Initially the object is at rest. So, initial velocity will be equal to 0. So, U equal to 0. U equal to 0. So, work done will be half into M V square. So, this is the equation to find kinetic energy. This is the equation to find kinetic energy. So, work done will be equal to half M V square. Half M V square, where M is the mass of the object, V is the velocity of the object. So, how we derive this equation? First we consider an object A. First we consider an object of mass M. Initially the object is at rest. So, its velocity is 0. Now, we are applying a force on this object. Due to the application of the force, its velocity changes from U to V. Its velocity changes from U to V. For this change in velocity, or to change that velocity from U to V, it travels a distance S. It travels a distance S. So, from the third equation of motion, we wrote it V square minus U square equal to 2AS. Then from that we wrote an equation like this, S is equal to V square minus U square by 2A. Name it as equation 1. Then from second law of motion, we know the equation F equal to MA. Let's name it as equation 2. Now, we know the equation to find work equal to force into displacement. So, we will substitute that for F, MA and S, V square minus U square by 2A. So, A and A will get cancelled. We get an equation like this, M into V square minus U square by 2. So, I split up into 2. Half into MV square minus half into MU square. That is, we know the object is at rest. Initially the object is at rest. So, U equal to 0. So, we got an equation like this. Work done will be equal to half mv square. That work done will be stored as the kinetic energy. That work done will be stored as the kinetic energy. So, kinetic energy equation is half mv square. So, here one important thing you can say, this one is, we can write it like this, work done, we can write it like this. We know the equation of to find kinetic energy is half mv square. Till here we derive. This work done will be stored as a kinetic energy. So, we will write an equation like this. V equal to half mv square minus half mu square. So, this one is also kinetic energy. This one is also kinetic energy. That is final kinetic energy minus initial kinetic energy. So, work done is equal to final kinetic energy minus initial kinetic energy, or we can write it like this, work done is equal to change in kinetic energy. Change in kinetic energy. Ke, that is a short form of kinetic energy. Work done is equal to change in kinetic energy. This is known as work energy theorem. That's known as work energy theorem. So, work done in moving an object from rest to attain a velocity v is stored in an object as its kinetic energy. The work done to move an object from rest to attain a velocity v will be stored in that object as its kinetic energy. That is equal to half mv square. Okay. Then we can write it in this way. Kinetic energy half mv square minus half mu square. Work done is equal to half mv square minus half mu square. Half mv square is final kinetic energy and half mu square is equal to initial kinetic energy. So, final kinetic energy minus initial kinetic energy, that is a change in kinetic energy. So, the change in kinetic energy is equal to work done, that is known as work energy theorem. Work energy theorem. So, here what will happen to kinetic energy if the mass of the object is doubled? If mass of the object is doubled, what will happen to kinetic energy? The kinetic energy also doubled. Okay. The kinetic energy also doubled. What will happen if the mass of the object is made to half? Then the kinetic energy also decreases. The kinetic energy also decreases. Now, what will happen to the kinetic energy if the velocity is doubled? Velocity is doubled. Yeah, the kinetic energy will increase by 4 times. V square. Okay, V square. That is kinetic energy is equal to half mv square. That is V equal to 2V. V equal to 2V. So, what will be the new kinetic energy? Half into m into 4V square. That is 4 half mv square. The kinetic energy will be increased by 4 times. Okay. What will happen when the velocity is reduced to half? then the kinetic energy also will decrease by 1/4. The kinetic energy also will decrease by 1/4. So, two factors are there that depends upon the kinetic energy. One is a mass and second one is a velocity of the object. First one is the mass of the object, second one velocity of the object. Thank you.